So welcome back, students. In the last video, we talked about the superposition of waves. Basically, we talked about coherent waves, coherent sources. So we said there could be two sources, S1 and S2. And these two sources are coherent if they have the same frequency, and then if they can maintain the same phase angle between them. For the second part, you have to imagine a point here. Let's say a random point P, and waves will travel from this source to that point, and another wave will travel from the second source to that point, and there the interference will take place. And then we said that the path difference between these two can be used to find the phase difference between these two forms. Okay. For example, I said if it is a, let's say like this is say 100 meters or something. Okay, this 100 meters. First one is 100, and then second one could be say 110 meters or something. So 110 minus 100 is equal to 10 meters. So that is the distance. That's the difference in the path lengths of these two waves. So this 10 meter, we are going to see how many cycles can be accommodated in the 10 meter. So the 10 meter, for example, can accommodate say maybe 23.4 cycles. Okay. So there is a difference of 23.4 cycles between this wave and this wave. So what it means is that this wave will reach here first. The first cycle will reach here, second cycle will reach, this would not have reached there. Then third cycle will reach there, fourth, fifth, sixth, seventh, ninth. So 23rd cycle will reach here. And when the 23rd cycle is 0.4 lambda into this, is when the first cycle will arrive there. The first cycle from S2 will arrive there. So that is the difference. So 23.4 is that. So for the first 23 cycles, they won't meet. And when they meet, the first one would have, they won't meet in phase. Like even when they meet, then they won't meet in phase because the 24th cycle would have covered say 40% or 0.4 lambda of that. Only then this will stop entering. So they meet there, alright, but when they meet, then there is this difference of 0.4 lambda. So you can always ignore the whole number and then you take the fraction. So that is going to give you the phase difference between one wave and then the other. And from that point forward, like now we said 24th is meeting with the 21st, and then 25th will meet with the second, and 26th will meet with the third. So then the interference will keep happening here from that point forward. So we said this. So this is how you do that. So this 10 meters, the path difference can be converted into a number of wavelengths here, and if you get a number of wavelengths, you ignore the whole number, okay, and then just take the fraction and then see what is going to be the phase for that fraction. So that is how it works. So we said, so this is how you find the phase angle between this and that. And there are some special cases, two special cases basically. In one special case, they meet each other in phase. Like suppose it's at 23.4, if this is just 23, then what would happen is that when the 24 starts, then the first will start there. We will start there. So as this is 0, this will also be 0. If this is 90, this will also be 90 at the same time. So, and from that point forward, the interference will keep happening for all the other cycles in the wave. Okay, if this is 23. Otherwise, if it is 23.5 or something, okay, then what happens is, the first one, the 24th wave, when it is at its, like it's at its peak, the first wave from here, that would be at its valley. So the peak will cancel with the valley. So that is, if it's 0.5, then they will exactly cancel. So this is called as destructive interference. The first one is constructive interference, where the two waves are in phase. And the second one is destructive interference, when the two waves are destroying each other. The peak of one wave meets with the value of the other, and any other angle. At any other time, the positive value will be cancelled by the negative value. So the net result will be 0. And that is what you call as destructive interference. I mean, if both the waves are of equal amplitude, that's important. If they are not of equal amplitude, then there will still be something left, but that will be minimum. In both cases, interference takes place, but in one case it's constructive, and then the other case it is destructive. So that's what we have discussed so far. We said for constructive interference, the path length difference, if I call this as d1, and then if we call this as d2, this length, then maybe d2 minus d1, the path difference, is going to be equal to n lambda. So whether it is 1 lambda, 2 lambda, 3 lambda, 23 lambda, 230 lambda, it will still be constructive. Because after so many lambdas, then these will start interfering in phase. So this will be constructive. Then destructive interference, d2 minus d1 is given by n plus f 2 lambda, or 2n plus 1 by 2 lambda. So again, in this case, n doesn't matter. This half is what is important. Okay, so because n just gives you the time delay in these two waves interfering. That's all there is to it. But once they started interfering, this fraction is going to matter. Okay, so this is what we did in the previous video. We just wanted to recapitulate that. But then you notice here, this is not the only point, right? This is not the only point. Like see, the light will go from these sources in all different directions. All different directions, right? Light could go here like that. Likewise, here also can do the same. I can go in all different directions. So I can take any point, any random point. For example, I can take this point in space. Okay? Then what is going to happen there? So clearly, this will send, I'll use a different color now. For this point, which I'll call as Q, then, so that is its D1, and this will be its D2. So maybe this is the path difference. Okay? This length will be equal, so this will be the path difference. And you need to see how many lambdas it can accommodate, and then you need to take the fraction, okay, to find out whether it's going to be what's going to happen here. Okay. So maybe if this is if this is going to be equal to n lambda, this length is going to be n lambda, then you will have constructive interference there. Maybe I'll take another point, PQR, maybe somewhere here, okay. I'll use a different color, okay. Point R, then also you see here that is D1, D2. So D1, D2. Note here, in this case this is bigger than this. So again, depending on what you are going to have, suppose you have n plus half lambda here, then I am going to have destructive interference here. Assuming that both the amplitudes are the same, then they will exactly cancel. So I will find a darkness, I will find a black spot here at this point. There will be no light. Here I will find a white spot, and here I will find a black spot, because this is constructive interference and this is destructive interference. But what did I say here? It is 0.4, right? 0.4 lambda. 23.4 is 27. It's not exactly 0.5. If it were 0.5, this would have been black too. But since it is 0.4, then that point would have some kind of a slightly more light than this one. Okay. Slightly, because I said this is black, this is dark. So this will be slightly more than that. You will have some amount of light, but not as bright as this. This will be the brightest, and this will be dark, and this will be slightly brighter than this. Likewise, all points in space will have this kind of a result. So even though we did it for just one point, you can see that all points, suppose I can take this point also here and then see what happens. The wave is going to reach here, and then the wave is going to reach here, and I can find the path difference between them, and depending on what I have here, whether it is n lambda or n plus half lambda, or like some 29.3 lambda, depending on that, my brightness could change here. So this is the brightest part, and this is the darkest part, and this point would be somewhere in between, and this point would be somewhere in between, and there would be some other point here again. PQR, I said this is S, right? So this is S, and that would be T. Okay, this could be T, and it is quite possible that these two, the waves that meet here, can have an n lambda thing, and this can also be bright. So you can have bright spot, and then dark spot, and maybe another dark spot somewhere here, and here again we have intensity which is between bright and dark. So you can see that all points in space will have different intensities. Okay, so this is what is called as the and if you look at it, then bright, dark, and an intensity, a certain intensity value. So it's all, I'm going to see a pattern in space. Okay, so this is what is called as the interference pattern. Okay. The best way to do would be to take this. I'm going to draw it now. So I have two sources. Now. S1, this is S2. Now, so let's suppose that this is going to send waves, right? This is going to send waves. Let's say if this is the peak, okay, and let us suppose that this is the valley of the wave. So it's one wavelength. So this is peak, and that is a valley. Okay, and then again this peak, and then this valley, then this peak, and this valley. Okay. So you can see, I can extend it, right? I can extend it. Okay. Something like this. So I can also extend this. So this is the wave traveling from this point. Something like this. And then valley, peak, and then valley. Okay, so this is from one source. I'm talking about this one. I can do the same thing for this source. Okay, so this would be its peak, and this would be its valley, and this would be its peak, and this would be its valley. This is peak, this is valley. Okay, this is peak, and this is valley. So note here, wherever the peak meets the peak, you will have constructive interference, clearly, right? Here, this is constructive interference. And then wherever the valley meets the valley, you will again have constructive interference. And the peak, valley, and then this one, peak. Okay. So I'm not drawing it properly, but you can see this. Okay. So it's clearly this has to go somewhere here. Okay. So I get this point, and this again. So you can see that, you see, okay, it has to be a straight line, but does not come out neatly. But if you draw it with proper distances, then you will get a straight line. You can see that you got the bright spots here. Okay, these are the places where you get constructive interference. But wherever the again, I can take here, right? So this is another constructive, 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 constructive. Okay, so this also, I'll use the same color here. Okay, so you can see the constructive interference. These are the points where you get constructive interference. But look at the other points like this, where you get the peak meets with the valley. This one, this one, this one, peak meets with valley. Here, here, here. So you get destructive interference there. So when you get destructive interference, I can draw so you get a destructive interference there. So that can happen other places too, right? So here, here, and here, 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 here. So these are points where you get destructive interference. As for my diagram, this is what it is. But if you really draw this with equal spacing, peak and valley, because like both this and this will have equal spacing, that is because they have the same frequency. So since they have same frequency, you will have same wavelength. Okay. So when this happens, you have, like your constructive and destructive interferences alternating. You can see a certain pattern there. Okay. I will demonstrate that to you with a short video after this. You can go through the video and then figure out how you can even create this pattern. Even in water wave will follow this. You can see that. And light wave also does the same thing. And that would be Young's double slit experiment. But we'll talk about that a little later. But you can see that when the waves interfere, constructive interference can happen at different points, and destructive interference also can happen at different points. So when you see that in real life, okay, it will form a beautiful interference pattern. I'll show that to you.
I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light.
Now that you've seen the interference patterns, let's get into the mathematics of it. So far we have talked about it in general terms, like I've tried to give you the physical meaning of all this. But obviously you have to quantify things in science, and that this is where mathematics comes in. Okay, so we are taking two coherent sources. Coherent sources. So let us say the first one is this y1 is equal to, say, a sine omega t. That's the first source. That's S1, right? So like that's the first source. Then the second one at a particular point, right? At point P. At point P, this will be the equation for y1, and then the second one would be y2. So that is going to have b sine omega t plus phi. So this is the phase difference we're talking about, and this phase difference would be constant at that point. So for these two waves, when they interfere, then they'll be constant. So that's the definition of coherent sources. We need to have the same frequency, and if the phase difference between them must be constant. Now, the point is, what would be the value at this point P? So let me draw it again. Okay? So I have S1 here, produces Y1, and maybe S2 here. This produces Y2, and then I'm just taking a point P, and I'm trying to figure out what would be the amplitude of this, what would be the value of this superposition here at this point P. That is what I want to figure out. Okay. So y1 travels here, and then y2 travels here, and we make there. So now y, which is at P, so you got y here, right? So y is equal to y1 plus y2, and this is actually a sine omega t plus b sine omega t plus phi. So that's my y. Well, I can do it, I can continue and then do this. There is a smarter way of doing it. Remember, in your electricity and magnetism, we came across what is called as a Phasor diagram. So what did we say? Well, you had a voltage for the across the resistor, and there was also a voltage across the inductor, and there was also a voltage across the capacitor. So they were varying in phase. They were all changing. The voltage across the resistor was changing with time, and the voltage across the capacitor was also changing with time. But how did we add them? we use a phasor diagram to add, right? So we said this. We said, okay, I'll do it here. So if this was my I, I just took this omega t at some particular point in time. This is where I see this. This is my I. If this is my I, then my V R was along I, and then I had this voltage. This was V L, and another VC was somewhere here. So you see it. Then I added them kind of vectorially to get to the final voltage. Which is the supply voltage, right? So that is how we did in the case of electricity, the alternating current. Listen, okay. I'm going to use the same approach because this is something similar. So this is also a sine wave. This is also a sine wave, and then it maintains a constant phase. A difference. It maintains a constant phase with y1. So it's more like I can take these two as phasors and add them. Kind of I can use vector algebra to add those. This is how I'm going to add. I'm going to take the amplitude of y1, which is A, and I'll take the amplitude of y2, which is B, and it's separated by an angle phi. I'm using a phasor diagram here. So clearly, then this would be the amplitude of the resultant wave. I'll call it as C. C will be Y. Okay, and I'll also have delta there, right? So in that case, my Y can be written as C sine omega t plus delta. That's my, after this manipulation, I get this value. Okay, but what is the value of C? We know this. C is given by this expression. C is actually square root of a square plus b square plus 2ab cos phi, the angle between a and b, not delta. Cos phi, a square plus b square plus 2ab cos phi. So this is going to be the resultant. Then delta, it's b sin theta by a plus b cos theta. That you can do that too. So you can find delta too. I'm not interested in that now, but you can find delta from your vector algebra. So this is the amplitude of the resultant wave. So you get this. So you see, you also get a sine wave. That is also a sine wave. When you add these two sine waves, you get another sine wave in different. Anyway, now you got the amplitude, and what would be the intensity? So what is intensity? Intensity is power per unit area. Then what is power? Power is energy per time. What are we trying to arrive at? We are trying to arrive at intensity. How intense this point is only. What is the intensity of light at this point? That's what we are trying to figure out. So that is I at this point. I is actually the intensity of Y, this way. Okay? And this one, I1 will be the intensity of S1. I2 will be the intensity from S2. The intensity contributed by S1 at this point will be I1. And the intensity contributed by S2 at this point will be I2. Then what would be the resultant intensity here? So I am trying to figure out. Is it going to be I is equal to I1 plus I2? No. y is y1 plus y2, so we started doing it, but then the amplitude C is not A plus B, it is something else. So I can also be different, so I am going to figure out how to calculate this. That's it. Okay. So I is the intensity of the resultant wave. Okay. And I1 is the intensity due to S1, and I2 is the intensity due to S2. So how are they combined? What is the relationship between the resulting intensity and the source intensity? So we are trying to figure out now. Okay, so intensity, as I said, is power per area, but power is energy per time, so it all boils down to energy. So we know from 11th standard that energy is proportional to the amplitude square, right? Even when we did our electricity and magnetism lesson, we said energy per unit volume, remember, energy per unit volume, this is not intensity, right? Energy per unit volume, U is equal to F into epsilon naught into E square. You notice, so energy is proportional to the amplitude square, but this is energy per unit volume. But then, if we include the length, then you are going to find energy per unit area. If energy per unit volume is proportional to E square, then energy per unit area, by deduction, should be proportional to E square. I am just giving you two ways of coming to the same conclusion. From your 11th standard, you know that energy depends on, is proportional to amplitude squared, and that's what you've seen in electricity and magnetism. Okay, so clearly, energy is proportional to amplitude squared. Notice it. Which amplitude? Is this the amplitude of the electric field or the magnetic field? Depends on both. Remember, in electromagnetic waves, you have both. Energy is equally shared between the electric field and then the magnetic field. So I can do it for the electric field, but then the same amount of energy is available in the magnetic field of the electromagnetic wave. Okay. So what I can conclude is that this energy, as I said, energy is proportional to amplitude square, which means power must be proportional to amplitude square, which also means that intensity must be proportional to amplitude square. So intensity is proportional to amplitude square. Okay, so now let's look at this. So what is the amplitude? What is the final? The amplitude of the resulting wave is C, right? So I must be proportional to C square. Okay, then I can have some kind of a constant there. It's clear. So this results in I is equal to some kind of K into C square. So what it is? I is proportional to this amplitude square intensity. Likewise, I1 will be proportional to A square. Then I2 is also proportional, I2 should be proportional to B square. So that gives you I2 is equal to K into B square. Okay. So if you can make use of this here, this expression. Okay. Now let's see. Let's try to express I in terms of I1 and I2. So I is equal to KC squared. So let me square this, C squared. So C squared is equal to A squared plus B squared plus 2AB cos phi. But what is c squared? It's I by k. What is a squared? I1 by k. B squared is I2 by k. So I'm going to use that here. So that gives me I by k, I1 by k, I2 by k plus 2 into, if a squared is I1 by k, then a will be square root of I1 by k, and b will be square root of I2 by k, and then cos phi. So this root k can be taken out. So this becomes I by k is equal to, let me take all k out, 1 by k into I1 plus I2 plus 2 root I1 I2 to cos phi. So k and k can cancel, so that gives me I is equal to I1 plus I2 plus 2 root I1 root I2 cos phi. So this is the most general equation for superposition of two coherent waves from two coherent sources. This is the most general equation. This works for any A, any B. Now I can consider some special cases. So special case is this. First case is special case. A is equal to B. The amplitude of y1 is equal to the amplitude of y2. So this results in I1 being equal to I2. Then what do you get? So now I is equal to I1 plus I1, because I2 is equal to I1, plus 2 into root I1. Again, root I2 can be written as root I1, then cos phi. So I'm bringing it here. So this is equal to, well, I'll do it here, then I'll probably next time. This is equal to 2I1 plus 2, now root I1 will be I1 cos phi. Okay, so this is for case where A is equal to B. If A is not equal to B, this will work. If A is equal to B, it gets reduced to this. Okay, so this is what it is. Now let's take the case where A is equal to B. If A is equal to B, then at different points, I'll do this. At different points around these sources, S1, S2, let me take this point P. A is equal to B, then what is going to be that intensity here? This point. Well, that depends on the phi these two waves make there. Okay? So if the phi is 0, constructive interference. If phi is 0, at all points where phi is equal to 0, constructive interference, these points, cos 0 becomes 1. So this equation becomes I is equal to 2I1 plus 2I1 into 1. Cos 0 is 1. So that gives you I is equal to 4I1. Notice here, this is I1, this is I2. Or if they're same amplitude, then this one and this one, if you take is I1, this is also I1. So when intensity, this is energy per area, energy per time per area, doesn't matter. Finally it comes down to energy. This energy and this energy you add, I1 plus I2, you are supposed to get only 2I1. How are you getting 4? Is it a violation of the law of conservation of energy? What does it say? If you add, energy can either be created or not be destroyed. You can only change from one form to the other. So if you have 2 joules and then another 2 joules, then you should get only 4 joules. You cannot get 8 joules. But you seem to have got 8 joules here. Why? Well, think about it. Think about the other case, where the phase is equal to 180 degrees. Then you get destructive interference. Then I is equal to 2I1. Now you get plus 2I1 to minus 1. So 2I1 minus 2I1 is going to be 0. So if I take another point, somewhere here, say Q, a point Q here, this I1 and this I1, they become 0 here. So if you take both the points, whatever you need to get, you get. There is no violation. So the energy that should have been here is taken out and put here. If you take I1, if this is I1 here, then 2I1 must be here. And this is I1 here, then 2I1 must be here. But what have you got here? You got a 0 here. Then where did the 2I1 go? It went here. So there is a redistribution of energy. Energy is not created here. There is no violation. What was supposed to be here is now here. Okay. So this has taken this energy also. So there is this redistribution of energy. So for constructive interference, you have this equation. I is this, and then for destructive interference, you have I is 0. So this point will be bright, really bright. It will be much brighter than and this would be dark. So you'll have a bright point and also a dark point. So there is a redistribution. Otherwise, what should happen? Take the energy, give it to all points equally. But no, interference doesn't do it. It takes energy from one point and puts it in another point. So this has 4 times the energy and this has 0 energy. So another constructive interference point will have 4 times energy and another destructive interference point will have 0 energy. So there is this redistribution. But if you take all the points together, the average is same, 2I1. Okay, so I want you to understand this idea. It's a very critical idea, so understand this. Well, now that I've talked about this, I have to talk about the coherent sources. But what happens in the case of incoherent sources? Well, in the case of incoherent sources, there is some trouble. What trouble is that? This phase is not maintained. This, like this, if it's 30 degrees, it's not 30 degrees all the time. It could be 30 degrees at one point in time, and then it could be 45, 20, 30, 15, and minus 20. You can have anything. But that is what incoherent sources mean. So, when it is like that, you see this equation is valid for only one instance. Correct? Because you see, when I have A and B, add A and B, A can be like this, and B is like this, and the phase phi is maintained, this is maintained, at this instant. when the instant changes, the next, this phase angle would not be maintained. At some other time, you may have something like this. This could be V and this could be A. So you can see this could be phase 1 and this could be phase 2, something like that. So you notice that this is changing. Okay. So in that case, this equation, this is always changing. Cos phi 1, like one instance it is cos phi, cos phi 1, another instance cos phi 2, cos phi 3, and you can have many different numbers. So what you do, you take the average. So when you take the average, this is how it is. I is equal to 2I1, or I say I is equal to I1 plus I2, general case, I1 plus I2, plus 2 into root I1, and then root I2. But now, I'll get cos phi 1 at one instance, cos phi 2, cos phi 3, that's changing, the intensity is changing with respect to time there. So then I'll take an average for this. So you know how to take the average, right? Take this function, find area under the curve, divide it by the time. But if you do that for a cos function or a sine function, what do you get? I'll call this as the average into cos phi. This is the average. So cos phi average function, average value, what is this basically? This is integral cos phi, or I'd say cos omega t dt. It's not a constant now. Cos omega t dt, we will do 1 by t. Right? So when you do this from 0 to t for one cycle, then this value becomes 0. Because this value becomes 0, the average value becomes 0, this term goes away, and simply, as far as the incoherent sources are concerned, you are going to get I is equal to I1 plus I2. So all points in space will have only this expression, I is equal to I1 plus I2. This is for incoherent sources. Incoherent sources. You're not bothered about them. But then it's better to note this. Why? Because there are two tube lights, two sources. If they were coherent sources, then one point should be bright, another point should be dark. So if you look at the wall, then you must have the interference pattern. But you don't find it. So the tube light is on now. You can see all white light here. Okay, all points. It's just white light. Okay. Again, if you take a tube light, then there are many sources, right? Many point sources in the tube light. So there is an interference that's going to happen because of all those point sources. Then why is not there? Because they are incoherent. I told you at some point in time, some part will be active and another part will be active at another point in time. So this point, the waves that come to this point would keep changing. Okay, so the path difference would not remain the same, so they are incoherent. The path difference does not remain the same, and the phase difference cannot remain the same. The phase difference does not remain the same, then you would end up with this kind of a situation. Cos phi, you need to take an average for the cos phi, because cos phi is changing. The cos phi is now a function of time. The phi is now a function of time. Phi is not a constant. Phi can be changing with respect to time. So then when you take the average, it goes away. So this is what it says. So that's why you say when you have two tube lights, even single tube light, just two point sources, when you shine light on a wall with those point sources, the intensity is a simple sum of those two light sources. You don't get an interference pattern there because those sources are not coherent. For the sources to be coherent, this cos phi, this angle, has to be maintained all the time at that particular point. So if the phi is 0, then this will be bright. If phi is 180, this will be dark. And if any angle between them, then you will have a varying intensity. So the intensity will vary from dark to bright along this way. So I want you to understand that. It doesn't violate the law of conservation of energy, even though it says I is equal to 4I1 instead of 2I1. Okay? It doesn't violate because it is taking energy from the dot point and putting that energy in the break point, at the break point. That is why it doesn't violate the energy. And this is for incoherent sources. You don't have to worry about that too much. I just wanted to let you know that why you don't find interference patterns in real life, and when you bring two sources, two bulbs, you don't see interference patterns all that easily. It's because of this, because they are not coherent. Interference patterns can be observed only when you have coherent sources. I hope this is clear to you.